Okay, welcome to class. Good to see you. Happy Wednesday, March 10th. Starting chapter 24, the Aldol chapter, continuing on with enolates and enols using carbonyls as nucleophiles. We also have quiz 6 for Thursday. It's on Learning Suite already. Make sure you print that out and take it before tomorrow. Also, we have the results from test 2. The average went up uh, quite a bit, I think, for the class. That's very, very impressive. As a class, you're doing very well. And all of a sudden, we had a couple hundreds, which is very good as well. And I like to point out the turnaround scores from test 1. And I promised you there'd be a number of positive turnarounds. So this is relative to test 1, how much better people did on test 2 now. Numerous people in double digits. So a lot of people in single digits turnaround. The real impressive ones are in the 20s, I think. There are 4 or 5 people with turnarounds of 20. There was a 22, a 23, a 25. And then the best turnarounds I could see were 27 and 33 points relative to test 1. So there's the proof that if you study, in a concerted way and keep going at it in a dedicated manner, you can easily improve your score. So still don't despair. If you're below this average here, you still have 2 midterms and the final, which is worth 200 points, right? So we have 400 points yet to go here. So even though we're about halfway through the material, you can turn around your score and do better. I have evidence for it. And the people I've talked to, if they've done better, they attribute it to more time studying or maybe adjusting the way they study, focusing more on the principles maybe, working more of the problems. Don't forget about the homework book challenge, which is due at the end of the semester. And that's your neat notebook filled with your answers to all of the even problems at the ends of each chapter. So it's not the end chapter problems, it's the problems that start at the end of the chapter. If you keep working those problems, that's a way to boost your grade if you're found in one of the cutoff regions at the end. And I'll talk more about that, but very good on that. Questions on anything there? Okay, so we've got a couple things here to review, I think, and maybe catch your attention. Um, Across the top here, we have methylphenol, paramethylphenol, and there's a couple steps there to convert it into this bromomethyl protected phenol, the TBS group, the silyl group on there. And then this is our electrophile, and then we're going to form the LDA uh, derived enolate of acetone. So we can go ahead and form that with LDA. And actually, then you dump in the benzyl bromide here. And this is a special type of benzyl bromide. It's TBS protected with a phenol right there. And then what's this reaction here? Well, that's our alkylation, right? That's a primary bromide. So we're forming the new bond right here. And then what's TBAF do? Remember, that's that fluoride reagent that takes off a protecting group. And we need that protecting group here because LDA would deprotonate that, and we get some other things going on there. So we keep that protected while we do the LDA enolate alkylation. And then this ketone right here comes from raspberries, which is kind of a neat compound. Sure, you can isolate it from raspberries, or you can make it synthetically. They're identical compounds that have the same properties and everything. Questions on that one on the top? How about these first 2 steps? Maybe the TBS chloride to put on the protecting group. And then what do we need here? We need to convert the methyl with light and bromine into the benzyl bromide. And those are kind of review. The key reaction here from chapter 23 is that one, right? The alkylation of the enolate. Okay. And what about this one? Here's another one from a previous chapter. Remember the name of that compound? Methyl what? Starts with an M. Methyl malonate. Yeah, the dicarboxylic acid. So it has these two hydrogens here. And anybody remember the pKa of those hydrogens? Let's see. Quite low, 10, yeah. So very, very good. And why is it so low? It's much more acidic than acetone, for example. The pK is 20. But these malonate esters, the pK of those alpha hydrogens is 10. And that's due to resonance, right? So the conjugate base is stabilized. So we can form that there and then do a displacement here. And then more base, do another displacement here. Those are both primary. And so what would we have here? We'd have the new malonate. Sorry, I didn't leave any room there. But I think you can see the propyls on there, and then this isobutyls on there. Okay. Oh, we need to see 3 carbons, 1, 2, 3. And then what's this? Urea. We're not hydrolyzing and decarboxylating. We're reacting it with urea. So we're going to get what? We're going to get the amide there, right? And you can see the malonate part here. And then whatever we put on the malonate, the propyl and the isobutyl will be on there. And that we said is one of those barbiturate drugs, okay? So this is kind of an added step. But it's something we know already, amide formation from esters, right? So you can kind of see how that's going to work. Now, if we take this same malonate intermediate and treat it with strong acid and heat, what are we going to do there? Well, the heat means we're going to lose carbon dioxide. Remember, what did we call that? Decarboxylation, okay? That's a special case where you have a beta carbonyl carboxylic acid. It can happen on either side. It's symmetric in this case. And then you see the carbon here that was that middle carbon of the malonate. And then it also has the isobutyl group on it. So 2 different products there. One is just trans amide formation, and the other is the decarboxylation of that. Okay. Oh, and now here's the new one for chapter 24. And this looks kind of strange, right? Although there is one reaction up here you should know or should remember. What's this? O3, ozone, right? What's ozone do to an alkene? Yeah, go ahead. Yeah, sure. It will split the alkene and make a carboxylic acid and an alcohol. Are you sure? Okay. Yeah, you'll split that. But remember, we just insert oxygen on both sides. So will it be a carboxylic acid? Or will it be, what, a ketone and an aldehyde? Okay. Yeah, that's okay. So we'll have a ketone and let's see, an aldehyde here. So yeah, if we split both the pi bond and the sigma bond, and then put in oxygen on either side, we'll get this aldehyde ketone. And we can form enolates there, right? And that's the topic here. So stay tuned for this. We're going to form, let's see, maybe an enolate here. A bunch of spots we could form enolates on either side of the carbonyls. And then we have one of them is the nucleophile, and then this, and that's the new topic, that we can use the carbonyl as an electrophile with an enolate. So it's the same carbonyl idea, but one's reacting as an enolate, one's reacting as an electrophile. You see that will form a 1, 2, 3, 4, 5 membered ring. Just right here. Here's where the aldehyde was. And we're going to lose water in this case. This is actually the aldol condensation you'll see in a minute. With heat here, with loss of water, you're going to get an alkene here. But that's a very different compound than our starting alkene, isn't it? So this is kind of a unique example. And we'll review other examples like that here in a second. But first, let's go up to the overhead here, Braden. See what we need to know in chapter 24 here. We've got aldehydes and ketone enolates. And let's see, so here's an aldehyde. Yeah, if we form the enolate there and then condense it with itself, we're going to form these aldol products. And that's kind of a funny word, aldol. It's one of these combination words that we use in OChem. It's a combination of what? Aldehyde and alcohol. So we smash them together and create the term aldol. It's actually an old reaction. It's been known for over 100 years. Now we know the mechanism and the general reactivity of it. But at lower temperatures, it can form these aldehyde alcohols, hence the name aldol. Or if we heat it up, higher temperatures, and we'll say 100 degrees for this class maybe. If you warm these up or let it go a longer time with the base, you can get the loss of water right here. And that's just an elimination reaction. So that's something we've seen before. But that product right there, and that's similar to what we just showed there, the intramolecular example. A lot of times the aldehyde's the same thing, and just one is the nucleophile, one is the electrophile. We can also have crossed aldols, where they're two different carbonyl compounds. We could have directed aldols where we use LDA first. We have asymmetric aldols with the chiral enolate, like the Evans alkylation. And then the intramolecular example, I think that's the one I showed here, although this one just goes to a dialdehyde with ozone. And then with the base at higher temperature gives the aldol condensation product. So you kind of have to track, where your nucleophile is and where your electrophile is and how that product arises, because it can be kind of confusing where that product came from. But we'll go through that. Now, if we have an ester, it'll be a little bit different. We'll do the Claisen product. We'll have an enolate of an ester, which will condense with an electrophile, a non-enolized ester. It'll form a beta keto ester, okay? And we can do other things there. The base will actually deprotonate the product. It actually sits like this. To get a favorable reaction, we'll have to have two enolizable hydrogens on the nucleophilic part. So some consequences to the mechanism we'll get into there. But that's a different type of product, okay? The aldol goes to an alcohol ketone, okay? The Claisen goes to a beta keto ester. And I'll point out the differences there clearly in the board here. Then we have an intramolecular Claisen here, beta keto ester again, with a diester. We'll show the biological equivalence of some of these reactions. And then we'll combine this reaction, the enolate of one acting as a nucleophile, with an enone electrophile, okay? And that adds here and gives this type of product. And that's a conjugate addition like the cuprates, okay? And then we'll combine the whole thing, the conjugate addition or the Michael addition, with an intramolecular aldol, and this is the notorious Robinson annulation. Now, if a student can master this mechanism and follow this, this is a very good indication of how well you'll do on test 3. This mechanism at first appearance looks very daunting, right? You have to master these first few reactions here. And then putting the whole thing together, this mechanism will be many steps. But if you keep track of it, where you form the enolate, conjugate addition, re-enolize, do the aldol, and then get the final product there. So don't be too intimidated by that. We'll go through it progressively and help you out. Now, we've looked at a lot of different carbonyl compounds, right? We've done a lot of different reactions with them. In theory, they can be the electrophile, right? Because that carbon of the carbonyl is partially positive, right? But we can also deprotonate at the alpha position and get it to act as a nucleophile. So how do we keep track of this? How do we not confuse all these conditions and not know why we're doing one thing over another? Well, here's your decision chart that kind of combines the ideas of these previous chapters with the one here going forward. When you get a carbonyl compound, identify that dipole. It's right here, the carbonyl, and it can be right here, depending on what that X group is, right? Is X a good leaving group? That's the first thing to ask, okay? If it's a chloride, a halide, or an anhydride, or a tosylated phosphate, yes, the pKa's of those conjugate acids are very low. That means what? The base coming off as X minus is very weak, right? So yes, good leaving group here. This is going to be the electrophile. We can add different nucleophiles and identify what the nucleophile is. And then here's our leaving group coming off, and we have acyl substitution. We have a new carbonyl compound based on our decisions up here of answering these simple questions, okay? Now, if X is not a good leaving group, okay, if it's an ester or an aldehyde or a ketone or aromatic ketone or an amide, those pKa's of those conjugate bases coming off are very, very high, or the conjugate acids, sorry. Those are not good leaving groups. Those would be very strong bases coming off, like a hydride coming off from an aldehyde. No way, you know, it's just too high. So these can be deprotonated, and LDA is your champion base there. If you want to form the enolate, that's the best way to do it. And then what? The enolate is now our nucleophile. It could react with different electrophiles. And it is different electrophiles, right? We alkylated, we halogenated so far. Now look, we're doing aldol and Claisen condensation, okay? So the decision chart kind of helps you correlate all these different reactions here. And you know, we also have the decarboxylation thing here from the malonate or the acetoacetate thing. And that's good to keep track of. And also with carbonyl compounds, the Grignards are kind of unique because if they add, and this is a good leaving group, right? If it's an acid chloride or an ester, we can add twice there with excess Grignard. So that's a little bit different reaction. But I think this chart and those couple ideas summarize everything on the carbonyl reaction. So it's good to have that. And of course, all my overheads are on Learning Suite. You know, if you want to see this chart, I saw a few people trying to write this down furiously. Don't do that. Okay, look it up on Learning Suite. It'll be there. Okay, let's go back here and get into the aldol and see what we need to know here. And maybe first, we'll still do a little summary here of the different approaches for these reactions. So if X here equals H or R, so an aldehyde or a ketone, right? And if we have the enolate of one of them, and what? This will be the electrophile, this will be the nucleophile, and that's often the key thing in this chapter, identifying which carbonyl becomes the electrophile, which becomes the nucleophile, because we don't have anything else in there now, okay? Before we formed an enolate with an alkyl halide or a halogen, and those were our electrophiles. Now we don't have any other reagents in there. We just have the carbonyl compound and we're treating it with base. One becomes a nucleophile, the other is our electrophile, okay? And so our intermediate looks like this. And that X, you see, is not a leaving group now, okay? If this is H or alkyl, if we tried to break down our tetrahedral intermediate, and there it is again, right? Your tetrahedral intermediate, that'll help you with the mechanism. We've seen that before. So that won't break down. If we just treat with water, we'll just get the aldol product, okay? And yeah, aldol, your alcohol aldehyde, okay? We can also heat this up and with more base, if we have more hydroxide, then we can get the eliminated product, which would look like this, okay? And whatever that X group was, if it's a hydrogen, it's just the unsaturated aldehyde now. Okay, so we're just keeping that generalized right now. So that's your aldol, okay? Keeping track of that one. Now the Claisen will be a little bit different. The Claisen, you see, we're going to have X equal to OR, okay? It's all the same carbonyl idea, enolate and then electrophile in one of them. But you see, we're going to get right here with our tetrahedral intermediate, and let's redraw it maybe with that as a potential leaving group, right? Okay. So that came from an ester, right? So we get to the same tetrahedral intermediate, and look what can happen here. under basic conditions, we can break that off. And what are we going to get? Different product. We're going to get the beta keto ester. Okay. And that's very different than these aldol products, okay, where we didn't have a good leaving group. So that I like to clearly differentiate what's going on there. All right, let's get into the aldol reaction with some specific cases and see what we need to know about this. Let's get one here. We've got an aldehyde, and we're going to react it with base, sodium hydroxide. And, you know, we're either in water or alcohol here. And, yeah. And if we keep this at 5 degrees, and that's an ice water bath, if we get too high of temperature, we can start to do the condensation, and we'll differentiate that, right? That'll be at higher temperatures. We'll say 100 degrees or so. But what's the first thing that can occur here? Well, we've got an alpha hydrogen. Now that pK is about 20, right? And so is this really favored? Let's see. We can take that proton off, leave the pair of electrons there, and get the enolate, okay? Now, that's freely reversible. This is a reversible base, so it's only, you know, a part per 1,000 or so forming the enolate. But what else is in there then? A lot of this, right? A lot of aldehyde that's still there. So let's go ahead and do the reaction there. So one is the nucleophile and one is the electrophile. Okay. You might say, well, wasn't that happening before in chapter 23? Yes, it could be, but we had a better electrophile then. We had halogen or an alkyl halide, primary halide. Okay. So that was a little bit different. So this is kind of the rest of the story. If you leave out that other electrophile, this reversible conditions, we have the undeprotonated aldehyde functioning as what? The de facto or default electrophile, you could say. Well, what's this product? Well, if we do that reaction, you see we get O minus there, and we get a new carbon-carbon bond. Now, once that forms, that's favorable, right? That's 90 kcals per mole. Even though this is a worse electrophile than we could say than a halogen or the alkyl halide, it still can function this way. And what? That begins to remove the equilibrium and drive it over here to this product. And so what do we do for the final step here? Well, there's water in there, right? So what's water going to do? Well, it's a proton source, right? And so what do we get? We get the aldol product. And you know, we draw it there, and these are the same aldehydes. This is propanol, right? So make sure you count the carbons and see. And it's always the, not the alpha, it's the beta hydroxy carbonyl product, okay? And you see, that's because we just made this bond. And here was our nucleophile. You can kind of see where everything still was. And here was our electrophile, okay? So that gives us that product. Let me give you an exact example of the yield here. And even this is backing up a little bit. If you take acetaldehyde with sodium hydroxide, okay? You don't need to draw 2 of them there, although we're using 2 of them in the reaction, okay? You don't need a 2 in the front here, okay? So 1, as it deprotonates, is going to add to this. And let's say 5 degrees here in water. And yeah, we get the aldol product, which is the simplest one, we could say. And it's 55%. Not bad, you know, these are both cheap starting materials. Most of these beta hydroxyaldehydes that are available commercially, they're all made using the aldol reaction. And even though the yield's not great, you can purify that and get a decent conversion over to that. Now, if we heat this same reaction up, and we can just start out at 100 degrees here, okay? We'll start boiling some of the water. We have a condenser on there so we can condense the solvent back in. The acetaldehyde, though, eventually forms this product. Now, That's different, isn't it? That's got the alpha beta unsaturated position here. And there you see the loss of water. In fact, the aldol product here is an intermediate for the aldol condensation product. And we'll call it that. This aldol condensation is with loss of water there. And it's this higher temperature that we need to have there. Let's look at a couple others of these. And we'll have to modify our mechanism to account for this loss of water here. How about butanol? Let's look at that one. KOH. You can use a different base here. Heat, or we'll specify 100 degrees C, just so you know here, okay? If we kept this cold, we would get the aldol product, right? The beta hydroxyaldehyde. But here now, we're gonna get the aldol condensation product. It's gonna look like this. And you can see right away, it's important to keep track of your carbons, right? Here we have 4 carbons now. Where are they all? 1, 2, 3, 4. That was what? That was our nucleophile. That's where our enolate was. Well, where was our aldehyde here? 1, 2, 3, 4. And there's where our electrophile was. And it indeed, because of the higher temperature, loses water and forms out. Well, how does it do it? Okay. Well, let's draw the aldol intermediate here. Sometimes that's called the aldolate before it's protonated with the water. And you can see as soon as we get water on there, we get the aldol product. And that's not the product we isolate. We need to get to the aldol condensation now. And you can see we need to pull this proton here. And we've got more base. So we're just reforming the enolate, right? Okay. So students are tempted to say, well, if we're pulling those electrons, can't we just push them over here and kick off hydroxide directly? Well, that would be actually a different mechanism. Let's see what the true mechanism is. The true mechanism is actually forming the new enolate. And it would look like this. Okay. And that pKa is actually a little bit lower. It's a little more substituted enolate now. Okay. That's part of why this works. Sometimes we add excess base. We'll add more base to get this to go. If you just show the higher temperature that's implied there, we won't get into the equivalence of the base or anything. But what you see is reforming what? The enolate right there. And we've got resonance there. We could draw that resonance structure. And now what do? Look, we generate more hydroxide, which is just the product from this deprotonation here. And that goes directly to the product, right? And generates more hydroxide, okay, from that water that we formed right there. Now, what are we going to call this mechanism? Okay, let's see. It is unimolecular. It just depends on this concentration. It's called an elimination, E1 and then CB. CB, what does that stand for? Before we learned what, E2 and E1 maybe? So you see the E1 part there. What do you think CB stands for? Conjugate what? Conjugate base, which is the resulting thing here. So it's this conjugate base that does this unimolecular elimination right here. If we did it this way, with this directly being deprotonated, we get the same product. But what would this be called? If the base directly pulls the proton and the leaving group at the adjacent position leaves, that's not an E1CB, that's E2. Somebody was flashing me the victory sign, meaning the 2 there. That's an E2 reaction. That does not occur. Why? How good of a leaving group is hydroxide? It's terrible. It's the worst one, one of the worst. So why is this working at all? Well, we are under basic conditions, and we're forming a new enolate right next door to this lousy leaving group. And that combination is the only reason why this can work. If you show this, you're implying that you can easily do an E2 on an alcohol. No way. Okay. You can't do a direct concerted E2 elimination on an alcohol because you're not invoking the stability engendered by the adjacent group here. The resonance, you need to think about that. We can have the minus charge here, and then we can use that minus charge to come back down and then kick off the hydroxide, okay? So that facilitates that as being a better leaving group. Now in 351, your instructor may have said, OH is never a leaving group. Well, never say never, like James Bond, okay? If you've got a combination here where we've got a stable enolate next door to a lousy hydroxyl leaving group, it still can work, okay? Yeah, question?
Is there water in the
Yeah, there's water, yep. So, you know, it's a very polar environment, which helps this come off too. It helps solvate that, helps it be a better leaving group with the polar solvent. Yeah, so the question is, was water in the beginning? Yeah, with KOH, you have to have water to get it into solution. It won't go into a non-polar solvent. But if you leave out the water solvent, you know, you can still depict the reaction there. Questions on the aldol and the aldol condensation? And are you okay with the leaving group issue here now? Okay. You can also do the aldol reaction under acidic conditions, and then you use an enol nucleophile and a protonated carbonyl as an electrophile. If I got time, I'll show you that mechanism. They tend to not be as useful or as high yielding. You know, the yields are already not great, 55% for the acid aldehyde. But you can do that same aldol under acidic conditions, but you'll have different intermediates, okay? Different nucleophile, different electrophile. If we got time, we'll look at that. Let's look at the intramolecular examples. These are kind of cool, I think. The aldol, I think, is right up there with the Diels-Alder and the Grignard as far as importance in OChem because it facilitates a lot of different type of products. It's very versatile, gives us a lot of synthetic flexibility. Let's look at some intramolecular examples now. And this is the one we caught your attention with there. Let's see. Let's take this, and we'll go back to the ozone thing. So here's dimethyl cyclopentene. And if we ozonalize that, remember we break both the pi and the sigma, as was pointed out, and then put in the oxygen on both sides, and we'll get this. We'll get a methyl ketone there and a methyl ketone there. And you might want to count carbons, make sure we got them all there. 7 carbons, 2, 3, 6, 7. Yep. Okay. And now we're going to treat with KOH and water and heat. So let's see, what are we going to do here? In general, ketones are not as good as aldehydes for the aldol, although under certain conditions, especially these intramolecular ones, ketones can be better, okay? But for simple ketones, they're more hindered, so they're not as good electrophiles. We'll see some examples, so especially intramolecular. So KOH, what are we going to do? Let's form the enolate. So I'm going to kind of abbreviate the mechanism here to move along. But you see, it's symmetric. Either one could do that, right? We could have the enolate over here, right? But let's see if we have it out here, then we're forming what? A 1, 2, 3, 4, 5, 6-membered ring. That would be favored. If we had the enolate over here, that would be a 1, 2, 3, 4-membered ring, intramolecular. Okay, so 6 rings probably better. Let's look at it and see here. Then we'd have this, right? Okay. And if we just protonated that, that would be our aldol product. Okay, but we're saying heat here. So let's see. Let's do a couple things there. Let's reform an enolate there. And let's protonate there. So yeah, I did a couple things there on the mechanism, I think you can see. And then the key thing is now that we have the conjugate base of the aldol product, and now we can do the unimolecular elimination. Okay, the E1CB. Let me emphasize that again. Don't do a direct E2 there. Okay, alcohols are not easily eliminated, right? Use the adjacent enolate to stabilize that negative charge, and then eventually it comes off. And what's our product here? It would be this. It'd be a cyclic ketone. Oh, and that methyl group is there. Okay. So just stitching that backwards, thinking about that, we just made those two bonds, didn't we? We did the elimination to put in the pi bond, and we made the sigma bond from the attack of the enolate onto that group there, okay? And that's a very different product, isn't it, than this starting material, okay? So the aldol's able to facilitate that. All right, the next challenge, crossed aldol. So far, they've all been the same. But now let's take two different aldehydes and react them under Aldol conditions. Let's see, which two do we want? Oh, we want propanol and we want acetaldehyde. Now, well, we're going to keep it at room temperature or 5 degrees, whatever. What are the products? How many products are we going to get? Let's see, we call this a crossed aldol because we have two different aldehydes. And this cross aldol. What should we do first? Let's see. Think of one as the nucleophile and one as the electrophile, and then mix it up. How many different ways can we mix it up? Anybody want to guess how many different possible products we can get here? Yeah, 4 products, okay. 4 maybe constitutional isomers, maybe. Because this one could be the nucleophile with that of the electrophile, or this one with itself, or this one could be the nucleophile or with itself. Okay, so that would be the 4 constitutional. What about stereoisomers, though? Are we forming stereocenters here? Anybody want to adjust their guess? How many total isomeric products might we get? Let's see. Let's just do the simple one with itself. So we'd have this one as a product, and that's acetaldehyde with itself. And then maybe let's do propanol with itself. So we'd have this one. And don't forget about the extra methyl on propanol. So those are the self-condensation ones, the one we've been doing. But let's see, we can also have this one as the nucleophile with propanol like that. Or we can have propanol as the aldehyde or the enolate with acetaldehyde. Are those the 4? Let's see, who guessed 4? Let's see if we can verify that. Is that the 4 you were thinking of? Yeah, so you can kind of keep it systematic there. But let's see, how many stereoisomers do we have here? That self one has what, 1 stereocenter? So that would be a mix of 2 what? Bl plus minus enantiomers, right? What about this one? Also plus minus there. That is indeed a stereocenter. Don't forget about the hydrogen there. And let's see, what about this one? Oh, there's a stereocenter there. These crossed aldols get more complicated. Well, this is a self one with this here, but because we have this methyl group here, 2 stereocenters. So how many total there? 2 stereocenters means 2 to the 2 power. So that'll be 4 isomers there. You can draw them all out if you like. And you can see them, you can have both back or both in the front, or one in the front, one in the back, or one in the back, this one in the front. There's 4 possible. 2 to the power of how many stereocenters you get is the possible. And same thing here, 2 stereocenters. So that's actually 4 there. 2 here on the top. So how many is total? 12 possible isomers. Okay, ouch. Okay, we're not going to keep track of all those. You should just be aware of those possibilities in the analysis of it. There actually are asymmetric versions of the aldol reaction, the Evans, the chiral enolates. We can form those, but right now we're not going to worry about that. How can we correct for this? This is a mess. Okay, if you did that reaction, it would just be too hard to isolate everything. How can we limit this? Well, let's have one aldehyde not have any alpha hydrogens. So one aldehyde can only be the electrophile. Okay, we'll limit it. No alpha H. Okay, and by having no alpha H, it can't become what? The nucleophile, the enolate. So that will limit it. Let's see this reaction. Let's take that same propanol, but let's react it with formaldehyde under the same conditions, sodium hydroxide at room temperature, or 5 degrees. So yeah, this could condense with itself, and we could get what? Some of this product here. But look, this is formaldehyde now with no alpha hydrogens, right? This has to be our electrophile. This can be our nucleophile or our electrophile, but which electrophile would be more reactive? Which one's less hindered? The acid aldehyde, right? So even though we're forming some of this and we can get some self-aldol condensation here, actually what turns out to be favored is this, because that's the smaller, more reactive electrophile in this case. And look at this, we actually get a good yield of this product. 63%, that's not bad after we purify it. And you can see, where did that come from? Well, it came from this right here. Okay, and it was lower temperature, so it didn't do the elimination there. Okay, gave the aldol product. And again, this is how we get around this problem of the crossed aldols, having one be your nucleophile and one be your electrophile selectively. All right, let's get into some other examples of this. So what other aldols will be productive here? Well, it's one where we clearly have one as the enolate and one as the electrophile. How about benzaldehyde? How can benzaldehyde participate in the aldol reaction? Can it be the enolate? Can it be the electrophile? What do you think? Yeah. Yeah, so the person that said it can't be the enolate because there's no protons to take off on that side, right? Let's react it with one that can, acetone. So here's a ketone doing it. And let's go to the condensation product, heat, see if we can come up with something. Now, acetone could be the electrophile, right? This is partially positive, but it can be the nucleophile. How good of an electrophile is a ketone compared to an aldehyde? Which will be the better electrophile? The less hindered aldehyde, right? So this could self-condense with itself, but I told you ketones are less reactive. They take longer times. Usually we have to add a strong Lewis acid and heat them up to go at all. Okay, but here we're heating it up. We're going to form this enolate. I think you can do that with hydroxide, right? And then here's our electrophile, and that's the only thing it can do, right? And we'll get this. And that would be our aldol product. But oh, yeah, we have heat. So what can occur? We can deprotonate here and then conjugate base and then eliminate. So what's our actual product? It will be this conjugated, you see, alpha beta unsaturated ketone with the aromatic group. And that's a very good yield. That's an 83% yield. Okay, let's turn this around and ask about this compound. Can anybody remember what that compound is? It's a very pleasant smell. We enjoy the taste. It's a naturally occurring compound. Yeah. Cinnamaldehyde from cinnamon bark. Yeah. So it's a flavorant, very common flavorant. And you see the aldol condensation stuff here, right? In fact, it'll be that same thing. It will be benzaldehyde. But what nucleophile now do we add? Not acetone. Let's see if we can figure that out. We still need a methyl group here to form the enolate, right? And then we need to do the elimination. So it's the same conditions here. But acetaldehyde, that would be a better electrophile, right? So this would condense with itself quite readily. But that is reversible. The aldolate actually is reversible. And then when you add here, and then eventually when you eliminate, why might cinnamaldehyde be the thermodynamic product in this case? Even though this could self-condense, eventually you get a good yield. Do I have the yield? 81% yield of this. Yeah. So why is this eventually? Well, look at the product, conjugated to the benzene and there and there. So this is unique. Once it reacts with that electrophile, thermodynamically, this will be more favored. So one other twist here, because we have a methyl ketone here, we can actually add more aldehyde, more base, and more heat. And you can get this kind of unique product where it's all fully conjugated. Look at that. And if that's the one you want, it can be formed at 87% yield if you do the reaction all the way across the top and just let it go with excess benzaldehyde. And that one you see is fully conjugated all the way through there. Okay. Now, one other question here. Okay, if acetaldehyde is good, how come we don't just keep going here? We can form more of this enolate and add more there. Well, we can limit the amount at 1-to-1 stoichiometry. But even if we have excess of this acetaldehyde, how come this doesn't add to just more there? And then it could polymerize in theory, right? It could just keep going. Why might that not work? Yeah, it's conjugated now, so that's going to be less reactive, right? You can draw the resonance structure this way and even use the electrons in the benzene ring. And by pushing those electrons into the carbonyl, it's less electrophilic now. The starting aldehyde isn't conjugated, so it's less electrophilic. So this thing of going on and polymerizing doesn't happen. Okay, don't need to worry about that. You can easily form those type of products. All right, let's look at one more here. Let's see what we're going to have. What if we have this aldehyde and acetophenone? See if you can figure out KOH at 5 degrees. What's the product? So 2 different carbonyls. See if you can figure that one out. And how about this one? Let's take an ethylated ketone, treat with LDA, and then acetaldehyde, and quench with water. What do we get? So there's 2 challenge problems for you today. LDA, we know how to form enolates with that, right? We don't have to use hydroxide. This is called a controlled aldol reaction, where we can form the enolate exactly where we want it. And that's what? This is now irreversible, right? Quantitative deprotonation. And where will it be? Here or here? And then we add in a second step, an aldehyde. So this will be our nucleophile. This will be our electrophile. Maybe that helps you out. How about that first problem? Have you identified your electrophile and your nucleophile? Formaldehyde can only be what? We just did one like that. Is it the electrophile or the nucleophile? What do you say? Electrophile, obviously. Okay. No alpha hydrogens, right? It's got to have another carbon on the side where we can form an enolate in order to be the nucleophile. This one certainly can be the nucleophile. Go ahead and form it, and that'll help you get to the product, I think. And then what's our temperature here? 5 degrees. So we're just going to condense there. Acetophenone is going to become this alcohol, right? And that's an aldol type product. At the beta position, we have a alcohol. Well, it's a ketone aldol, but it's in the same family of names here. This could have been the electrophile also. It could have condensed with itself. But look, formaldehyde's very, unhindered, very faster as the electrophile. And so as that enolate forms, the quicker action will be with that, the crossed aldol in that case, right? These are both crossed aldols, right? All right, how about the controlled aldol with LDA? What's our first step there? Enolate on the left or enolate on the right? What do you say? Who says on the left? Who says on the right? Okay, everybody, very good. And that's the less hindered one because LDA is bulky, right? So that's the only spot you form the enolate. You can do this at minus 78 degrees, keep that cold. You can use a different solvent now, THF, okay, which is the ether there. You have no proton source, it's not reversing. Then you dump in the acetaldehyde, also in THF, and what? You get the aldol right here, right? And then you crunch with water. Let's see if you got your product okay. The ethyls still going along for the ride on the left side. And on the right side, what do we have? Our aldol product. And don't worry about the stereochemistry here. We have a possibility of what, 8 different isomers here. We'll just be concerned with the constitutional isomers. You should be aware of the other isomers. That's an advanced topic. We won't get into that. But what bond did we make right there? Okay. And what enolate did we make? We made the less hindered enolate and then reacted with the better electrophile, the aldehyde in that case. Questions on any of that? I think that's good for today. We'll get into the Claisen next time, and eventually the dreaded Robinson annulation coming up. Okay. Practice these aldol reactions, and we'll see you next time. Thank you.